As an example of using conservation of energy, we have a little problem here with it's sort of like a roller coaster. So we're going to have a block with some initial velocity, so some initial kinetic energy at this level. It's going to go down, come back up, and then all along this track until this part. So all along here, the friction is 0, so it's only conservative forces doing work, so only gravity is doing work. And then there is friction, kinetic friction coefficient of 0.6 as the block slides for a distance d and then comes to rest. So we want to use conservation of energy to tell us how fast is the block moving when it gets to the start of the frictional track, and then how far does the block slide as the force of friction is doing work on the block. All right, so I'm going to go through and talk about the 3 different states I'm going to use. So it's a conservation law. Conservation laws connect different states together with the conserved quantity being the same in each state. So I try to be careful. State 1 is at the start of the track, and all energy is kinetic. And state 2 will be up here, so we can answer that first part. At highest point on track, and mechanical energy is still constant. And the final state is the block at rest after it is slid across the part of the track with friction. The block at rest, all mechanical energy is gone. And to work against friction. All right. So in state 1, all the mechanical energy is kinetic, because I'm going to pick this to be my 0 level for gravitational potential energy. So there's state 1. State 2, still have conservation mechanical energy, so that is going to equal kinetic energy 2 is gravitational potential energy 2. That's when the block is there. And then state 3, there is no mechanical energy left anymore, as the block has skidded and now it's at rest after skidding a distance d. All right. So let's use conservation of mechanical energy to get the speed of the block here in state 2. So we are saying that kinetic energy in state 1 is potential energy in state 2 plus kinetic energy in state 2. We can write that out. Half m v1 squared is going to be equal to m g h plus a half m v2 squared. And then everything has either inertial or gravitational mass in it, so we don't need to know the mass of the block. And we can solve for V2. That is going to give me, move this to the other side, multiply everything by 2. We have v2 squared is v1 squared minus 2gh. Then to get v2, take the square root of both sides. And just pop in numbers. And plus minus 6 meters per second quantity squared minus 2, 9.81 meters per second squared, and that height was 1.1 meters. So it does make it that high. I won't wind up with an imaginary number here. And then obviously we're asking for a speed, so it's just the plus sign that makes sense out of the two possible roots. When I do that, I got that to be 3.797, so we'll just call that 3.8 meters per second. So that answers the first question. Now, how far does the block slide? This is your Indiana State Police forensic investigation question. How far is the block going to slide? So the mechanical energy of the block is going to be all used up into work done by the force of friction. Flip over to another sheet of paper, a little bit more room. And I'm going to do this with friction being internal to my system. Just for the sake of presenting something. I could have it be on the other side of the equation and that would work out as well. So, no work done by external forces. It's going to be the change mechanical energy plus the change in thermal energy. And then we'll compare connecting state 1 with state 3. So we expand this out. I have K3 minus K1 plus U3 minus U1. So that's all from the change in mechanical energy plus the change thermal energy. That was where we picked our 0 point for gravitational potential energy, and the block ends at rest, so I know that that has to be 0. I move K1 to the other side, a half m v1 squared will be mg h3, which is just h, and then the change in thermal energy is going to be the force of friction and how far it slides. Substitute in what that is. Half m v1 squared is mg h3 plus force of kinetic friction mg d. M cancels out. the thermal energy is going to increase by the work done by friction. Okay. So simplified, I have half v1 squared, so g times h3 plus coefficient of kinetic friction g times d. I'm going to get the term with d by itself on one side of the equation. Move that to the other side. Coefficient of kinetic friction times g times d is v1 squared over 2 minus g times h3. And then divide both sides by coefficient of friction times g to give d by itself. 1 over mu k g v1 squared over 2 minus g times h3. All right, and we're ready to plug in numbers. Let's manipulate just a little bit more, then get a g to cancel out. Okay. And then when I put in values for that, that is 6 meters per second quantity squared over 2 times 0.6 pure number g 9.81 meters per second squared. And that does work out to be a distance, so that's good. Dimensional analysis. And we've got 1.10 meters over 0.6 pure number, and get that to be 1.2 meters. And if you think about the structure of this equation, I'm going to make sure everything makes sense. The more kinetic energy it had initially, the greater this d is going to be, but the higher up it went, the smaller d is going to be. And so that's why this comes in with a minus sign. And then having a smaller coefficient of friction is going to amplify the effect of both of these terms. So you're dividing by the coefficient of friction. So even when you get an equation, it's good to think about what the equation is telling you. If you think about the limit of where a different term gets bigger or smaller, in addition to thinking through, does everything have the right dimensions? If d is a distance, then every term that I have over here, like this first term has to turn out to be a distance, and the second term has to turn out to be a distance. So it's a good way to check that you have things set up correctly. Dimensional analysis won't guarantee that you don't have a mistake, but it will catch a lot of the mistakes that people are prone to make.